Alright, in this video, this is the first of several where we're going to talk about confidence intervals. And in this video, I'm just going to give you an overview of the terminology and what confidence intervals are all about. And then I'm going to have a couple of videos after this where we actually do some examples and look at the specific mechanics of making a confidence interval. But in this video, we're going to do everything else. We're going to make sure that you understand what we're doing and why. So to get us into the mindset of what we're going to be doing when we are talking about a confidence interval, what we're doing is we are collecting data on something that we want to learn about. And there are two categories of things that we might want to be learning about that we're going to be discussing. One thing we might want to learn about is a mean. So we might want to know information about a mean of some population. Maybe the average income, or the average age, or the average wealth, or the average years of education of some population. So that might be one thing we want to learn about. Another kind of thing we might want to learn about is a proportion. And a proportion is going to be when we're trying to ask people a question that's a yes or no question. That's the easiest way to think about it. So, for example, what proportion of people are female? What proportion of people have a college degree? Or what proportion of people are unemployed? So, here we're going to take the number of people who say yes to a question. This is the basic way you calculate the proportion. How many people say yes, I'm unemployed? Yes, I'm a female, or yes, I have a college degree, divided by the total number of people that you ask. So this would be the total number of people sampled, and usually we think about that as n, small n. How many people are we asking this question to? Now, after we take this sample of information, what is the first thing we're probably going to do? Well, we're either going to calculate this proportion of people who say yes, in which case we're going to call that a p bar. P bar is what we call the sample proportion. Sample proportion. And it's important that we understand some other terminology related to what we're talking about, because we're going to hear these words a lot. Now, if we take a sample of people and we calculate the average of the sample, right, the sample mean, then the symbol we're going to use for the sample mean is X bar. So kind of like P bar, that tells us it's a proportion calculated from a sample. This is a sample mean. This is a proportion calculated, a mean, an average calculated from a sample. Now, it's important to know, what are we doing here? Why did we calculate this average of a sample, or this average of a proportion? Well, what we call these things, the sample proportion or the population proportion, are point estimates. Point estimates. Now, why would we call it a point estimate? Well, because what these numbers are, suppose we calculate that the sample average, number of years of experience in a certain sample that we take from a larger population of people, we find that the average number of years of experience in our sample is 23.2, a lot of years of experience. The sample mean is a one number. So if you think about it being on a number line, it's one point on that number line. And you can think about that as being our best guess. Our best guess at what? Well, what we're trying to learn about is the population mean. So this sample mean is an estimator of the population mean. We don't know what that is. That's why we're calculating the sample mean. That's why we're collecting the data to begin with. Similarly, with the sample proportion, we could find that, for example, 50 out of 150 people in our sample, which would be a sample proportion of 0.33, have a master's degree, for example. So our point estimate, our one best guess is as to what the true proportion of all people who have a master's degree would be that 0.33. But that's not the truth. That's not the real proportion of everyone. That is something we're just using to estimate so it's a point estimate, again, of what we call P, or some people will use the Greek letter rho for the true population proportion. And so P equals, well, we don't know. That's the whole point of collecting the data to get a proportion of a sample, is to learn some information about what the truth might be. And our one best guess, the point estimate, would be 0.33, and that's a good start. But we want to be able to do a little bit better. Now let me go ahead and review a little bit of a few other vocabulary words that you'll see thrown into the mix when you're talking about confidence intervals and point estimates. So another word to remind ourselves of is this X bar and the P bar. These are things that we call sample statistics, because these are things that are calculated from a sample. And the word statistic, if you're taking a statistics class, the word statistics, misspelled it there. The word statistic really means estimate. So these things are estimates. And what are we estimating? Well, the things that we're estimating are the true things that are about that population, the mu or the P, and those things are things we call population parameters. These are the truth. These are the things we're trying to learn about. So parameters are the true things, and the statistics are the estimates. So think about this as being the truth. What would the real answer be if we had all the data for the whole population? Now another couple of things to throw into the mix here while we're talking about them. Another sample statistic that you should be familiar with is S. That's a sample standard deviation. And we calculate sample standard deviations to learn about sigma. What might the population standard deviation be? So S is another sample statistic. It's an estimate. And sigma, the population standard deviation, is the truth. That's what you would get if you had all the data for the population. Now, what we're going to be doing here is taking these point estimates, taking the X bar, taking the P bar, and giving a little bit more information about these point estimates. Namely, how close do we think these point estimates are to the truth? This is a very important question to answer. If you tell me that you went and collected some data and your sample mean was 23.2, most people in statistics and most people who are scientists will tell you that if you just give me a point estimate without giving me any kind of indication about how accurate you think it is, and when we say accuracy, what we mean is how close do you think this sample mean is going to be to the truth, then it's worthless, right? Because you could just make up a number, 23.2, and if we have no idea how accurate or how close that might be to the truth, it really doesn't help us understand what the population mean is. It might be better than nothing, but it's not really all the information we need. We need to know how close we think we are. And also, what we want to try to do here when we make these confidence intervals is to make a range. So not just one number, a point, but an interval, say between 22 and 25 or 21 and 26. And make an interval where we think the true mean is, So that's one thing we want to do, or make an interval where we think the true proportion is. But also give a number that quantifies. How sure do we think we are that the truth is in that interval? Right? So how confident are we that we think the truth is somewhere in that interval? Okay, so let's move on here and talk about these confidence intervals a little bit more. So let's move down just a little bit here so I have a little more space to work with. Let me change color here since we're kind of moving on to a slightly kind of a next step in our discussion here. When you're talking about data, you want to know not just the mean of your data, but you want to know the standard deviation of your data, right? Now let's make sure we understand what a standard deviation means. And whether it's a sample standard deviation, that's an estimate, or whether it's a population standard deviation, that's the truth, that's the real deal. What the standard deviation is trying to tell us is a common distance that an individual in that population, so it's kind of a common distance that an individual is going to be. So here's the way I think about it. A common distance between an individual that we randomly select and the mean, right? And the population mean, or the sample mean. Either way you can kind of think about it. So for example, for adult men in the United States, the population standard deviation, as best we can tell, is about 3 inches. And so what that tells us is, if I randomly go and pick an adult male in the United States, that it's pretty common for that one person to be within 3 inches of their height, that individual, and the truth. Sorry, as I'm talking here, I'm making some spelling errors. Let me try to correct them. Individual and the truth. All right. So it's common for an individual person to be about 3 inches away from the average. It's less common, but still happens, that sometimes somebody would be 6 inches above average or 6 inches below average. But what we mean by common distance is most of the time people are going to be within one standard deviation. Now, especially if we're talking about things that are normally distributed, have one of these bell-shaped distributions that we talk about so often when we're doing confidence intervals or talking about sampling distributions. So a standard deviation tells you a common distance between an individual and the truth. Now, something that when you're talking about sampling distributions, that's the next thing. Let's review here very quickly. A sampling distribution. A sampling distribution tells you how likely is it that your sample mean, so let's just use sample means as an example here, how likely is it that your sample mean is somewhere within some distance of the truth? So it tells us a distribution of, if I go out and collect sample means, how close are they likely to be to the truth? And sometimes sampling distributions have a normal distribution. Sometimes, not always. And we'll talk more about that in just a minute. So sometimes we can use a normal distribution to talk about how sample means are distributed around the truth, how close they are. And same thing for sample proportions and the true proportions. Now it turns out most of the time we're going to use the normal distribution in this case, but it all depends on the particular situation. And we'll review those rules in just a minute. Now, when we talk about sampling distributions and how close a sample mean is to the truth, or how close a sample proportion is to the truth, let me move down a little bit more here. A measurement that we use to talk about how close a sample mean might be to the true mean, or how close a sample proportion might be to the true proportion, is called a standard error. Standard error. A standard error is something that we want to calculate, and instead of using a symbol like this, the population standard deviation, we have two different symbols we use depending on whether we're talking about a sample mean or a sample proportion. But a standard error tells you a common distance. It's like a standard deviation, a common distance between your estimate and the truth. So it could be a common distance between a sample mean and the true mean, or a common distance between a sample proportion and the true proportion. So most of the time we're going to be how close between our estimate and the truth. And the standard error for a mean, you get it by taking the standard deviation, the common distance between individuals and the truth, and you adjust it by dividing it by the square root of the sample size. How many are in your sample? And so this standard error is going to get smaller as your sample size gets bigger. Your common distance between your estimate and the truth. And why do we call it a standard error? Well, because if your sample mean is not the same as the true mean, in some sense that's an error. You were wrong. Your estimate was wrong. And so the standard error just tells us a common sized error that you're going to be making. Most of the time will be about this far away, or less than that far away. For proportions, the formula is you take the p, your population proportion, or your best guess at what the population proportion is, p times 1 minus p, divided by n, and then you take the square root of the whole thing. And actually these two formulas are the same thing. On the top, it just turns out that for proportions, the square root of p times 1 minus p gives you that standard deviation for proportions. And then we're dividing it by the square root of n. But it's more convenient usually to just take the square root of the whole thing after you calculate p times 1 minus p and divide it by n. So these things are standard errors. They're common distances between an estimate and the truth. And sometimes, as I said, the distances between estimates and the truth have a normal distribution. Sometimes they don't. Now, when can we use the normal distribution for these things? And when can't we use the normal distribution? Well, before we get into that, let's talk about what if we could use the normal distribution. Suppose we could. Many times we can. Well, normal distribution has a bell shape like this. What we're saying is, if this is the truth, then these common distances, these standard errors, means that most of the time, if we're having a normal distribution, that we'll be within the mean plus one of these standard errors. Let's just say it's a standard error for a mean, and the mean minus one of these standard errors. And if we're using a normal distribution, this standard error acts just like a standard deviation. In fact, it is a standard deviation. That's the reason we use this symbol. It's a standard deviation for sample means. What percentage of the time, if you're using a normal distribution, will you be within one standard deviation of the center of that distribution? Well, if you look it up on the normal distribution table, you'll find that 68.26% of the time you'll be within one standard deviation. So within one of these standard errors in this case. Now, and 68.26% of the time, what will be within one standard deviation? Well, the sample mean, right? Because that's what we're talking about here. The sample mean will be somewhere in here within one standard error below the true mean or one standard error above the true mean, 68.26% of the time. Now, if you want to make the most simple kind of confidence interval, the simplest kind of confidence interval is just to say, okay, here I have my sample mean, and I'm going to add and subtract one of these standard errors. And if you do that, what you can kind of say is, well, if this tells me a common distance that my sample mean is from the truth, and 68% of the time, right, it'd be actually 68.26% of the time, you're telling me that my sample mean will be within one of these, of the being, of the truth, then you can make a 68.26% confidence interval simply by doing this formula here. It's the sample mean plus or minus one standard error. Okay? Now, what if we wanted to make a confidence interval where we're more confident? Well, actually, the most common kind of confidence interval that people make when you read scientific studies is a 95% confidence interval. Okay? So, what if we wanted to make a 95% confidence interval? How would that actually be done? Well, let me draw a picture here to show you the general idea. If you want to make a 95% confidence interval, let me draw this x-axis a little flatter here. Then what you do is you say, okay, we want to be 95% confident. Then another vocabulary word you'll hear mentioned quite often is, well, if we're 95% confident, then 0.95 is what we would call our confidence coefficient. Confidence coefficient. That just means that the area that we want between, in the middle here, is going to be 0.9500. And if we want 0.95, 95% of the probability to be in the middle, our confidence coefficient, then there's this thing that we call alpha, and that is basically how unconfident we are, how not confident we are. So it's 1 minus the 0.95. 1 minus 0.95 equals 0.05. So that's what we would call our alpha in this case. Now, alpha just gives us the total area that's not in the middle. And if it's 0.05, what do we do with that information? Well, that means that half of that alpha over 2, is going to be here. Half of that alpha is 0.025. Half of that alpha over here in the bottom tail, 0.025. What if we wanted to make a 95% confidence interval? Well, we're not going to use one standard error. We need to go to our z-table and figure out how many standard deviations do we need to go above and below the center in order to leave 95% of probability in the middle. And the easiest way to do that is to take this 0.025, which is alpha over 2. Take that to the normal distribution table and find what z-score would leave 0.025 in one tail. Now, I'm going to assume you know how to use a z-score table, and that z-score that you're going to find is z equals 1.96. So, when you're making a confidence interval, if you want to make a 95% confidence interval or any other kind of confidence interval, the formula is, just to change this formula here slightly, that would be for a 68.26% confidence interval. In general, we just say, well, use whatever z you want there. Doesn't have to be 1. You don't have to be 68.26% sure. You can put any z here that you want. If you want to be more confident, use a z of 1.96 and you'll be 95% confident. Now again, confident of what? Well, you'll be 95% confident that the true mean is somewhere in this interval. So we would plug in 1.96 for that z. Now, another bit of notation that sometimes people will use when they write down the formula for a confidence interval is they'll put a little subscript there, alpha over 2. And all that alpha over 2 business, it's just a subscript. That's just telling you what z-score are we going to use. Well, we're going to use the z-score that leaves alpha over 2 in each tail. And it's that alpha over 2 that we're going to the table to use to look up the z-score to use. All right? So let's just put some numbers to this and do a quick example without really doing any computations. And then in the next video, we'll actually look at some practice problems, and we will solve to see how this is actually done. So we take the sample mean plus or minus z times the standard error. So let's looking at a very simple case. Suppose z is 1.96. Then suppose, like in our situation we had above here, suppose we had a sample mean of 23.2, and suppose it just worked out that our sample mean was 23.2, and then we calculate our standard error using this formula right here. We just calculate that. And when we calculate our standard error, we get a number that is 2. It just happens to be 2.00. Just simple number. Not normally going to be a simple number like that after we calculate it. But we get a number like 2.00. And we know that our z-score we should use, alpha over 2. So in this case, if we're making a 95% confidence interval, some people might say z.025. Right? That is the z-score we're using is 1.96. So we would make our confidence interval, and we would say we are 95% sure that the true mean of this population is 23.2 plus or minus 1.96. That's the z-score times 2.00. That's the standard error. We're assuming that we calculated here. And so then we just see, well, what is 1.96 times 2? 1.96 times 2 equals 3.92. And that quantity, not 3.22, 3.92, that quantity 3.92 is what we call E, or the margin of error. Margin of error. And you see here the margin of error depends on 2 things. The z-score, which gets bigger as we want to be more confident. We're going to make that confidence interval wider. We're going to use a bigger z-score to get more area in the middle. And it also depends on our standard error, which is going to get smaller as our sample size gets bigger, and bigger as our sample size gets smaller. And so we would say, here's our 95% confidence interval. We are 95% sure that the true mean is 23.2 plus or minus 3.92. And that's one way that people will leave the answer. They'll just say, there's our confidence interval, 23.2 plus or minus 3.92. Another way you'll see people write confidence intervals is they'll go ahead and add and subtract that 3.92 from the 23.2. So let's just do that. So we could say our 95% confidence interval is 19.282, and then we add the 3.92 to the sample mean. 23.2 plus 3.92 equals 27.12. Now let me say it again. I've repeated this a few times, but we are 95% sure that the population mean is somewhere between 19.28 and 27.12. Now, on multiple choice tests, a lot of times you'll be asked the question, what are you 95% confident of? Don't say that you're 95% confident that the sample mean is somewhere in that interval. We know that the sample mean, at least our sample mean that we got, is in that interval. How do we know that it's in our interval? Because when we made this confidence interval, we put it right in the middle, right? 23.2 is exactly in the middle between these two numbers. So we know our sample mean is in that range, but it's the population mean that we think there's a 95% probability is in there. That's pretty sure. That's pretty confident, okay? And we can do the same kind of thing for a population proportion kind of question. We have a sample proportion. We calculate a standard error. We find a z-score, and we take the p-bar. We could take a p-bar, sample proportion, plus or minus a margin of error, e. And a margin of error is always, we take a z-score, some multiple, could be 1, could be 2, it just depends on how sure you want to be, times that standard error of proportions in that case, okay? So I'm going to end this video here, and then in the next video we're going to look at sample means and how to make confidence intervals with sample means.